So we're continuing with solving linear systems of 3 equations and 3 variables. We already did one example when we used the row reduction method and arrived at a solution. The example that we did when we introduced the row reduction had a unique solution. That means there was only a value for x, only a value for y, only a value for z. Now, is that always the case? No, that's not always the case. We can arrive after row reduction, we may arrive at a contradictory result. That is a contradictory equation such as 0 is equal to 5. That means that the system is inconsistent, means there's no solution. We can reduce the number of equations. Here we have 3 equations and 3 variables. We can reduce the number of equations to, let's say, 2 equations. That means there's less restrictions on the system without arriving at any contradictory results. Then it means that we have infinite solutions. And the last case that is mentioned in this list is the case that we already gave an example for. Now let's do another example to demonstrate the other 2 cases. This example is x plus 5y plus 4z equal to 5 and 2x minus y minus 2z equal to 10 and 3x plus 4y plus 2z equal to 15. As usual, we continue with the method of row reduction. What I want to do is to create a leading one for x in the first row. That is already done for me. So the next step is to create to make the coefficient of x 0 underneath that leading 1. To do that, I have to add a multiple of the row with the leading 1 to the row that I want to eliminate x in. In here, that means row 2 plus negative 2 times row 1 should go to row 2. That is, row 1 doesn't change. Row 2 on a little piece of scratch paper is going to be, this is row 2, the original row 2. Negative 2 times row 1. Add them together. This becomes 2x minus 2x becomes 0. This becomes negative 11y, negative 10z equal to 0. So row 2 becomes negative 11y minus 10z equal to 0. Row 3 does not change. So we eliminated x in the row following the row with the leading 1. Now we need to eliminate x in the third row as well. Again, use the row with leading 1 to eliminate, for x, to eliminate x in the third row. That would be row 3 plus negative 3. Row 1 has to go into row 3. On piece of scratch paper, row 3 is 3x plus 4y plus 2z equal to 15. negative 3 times x, negative 15. Y minus 12. Z equal to negative 15. And adding these two cancel each other. Negative 11y, negative 15 and 4, negative 12 and 2 is negative 10z. So the new equation is the first row stays the same. The second row stays the same. The third row is going to be so if we want to continue, and this is actually a good idea, if you want to continue with the method of bookkeeping that we discussed, the next step is to create a leading one for y, because we created leading one for x, we eliminated x in other the rows that come after. Now it's time to create a leading one for y. And so to do that, we need to divide row 2 or multiply row 2 by the reciprocal of the coefficient of y and put it back into row 2. This will give me, I don't need scratch paper for this one, x plus 5y plus 4z equal to 5. Row 2 becomes y plus 10, 11, z equal to 0. And then row 3 does not change. The next step is to eliminate y in the third row. If I'm eliminating y in the third row, what I need to do is use the second row, which contains the leading one for y, and eliminate y in the third row. I'm going to erase the board, come back, and continue. So we reduced, in the process of reducing this system, we arrived at this row equivalent system. And before erasing the work, I put it up here. I copied what we got from the last time over here. So the next step is to eliminate y underneath the y with the leading one. How do we do that? Use that leading one to eliminate y in the third row. That is row 3 plus 11 row 2 goes to row 3. Scratch paper work. Row 3 is this. Multiply row 2 by 11. And it gives you 0 is equal to 0. So we end up with this system. First row does not change. Second row changes to, does not change. The only row that is changing is the third row. So here we reduced the system into a system of 2 equations and 3 variables. There's no contradictory results. This is the reduced form because I get the maximum number of leading ones I can create in here. 1 for x, 1 for y. And then underneath every leading one, there are zeros. So this is the reduced echelon form of the system. So the next step is, first of all, recognizing that we're actually in the case 2. There are infinite solutions for this system. The next thing is to choose a parameter to solve for x, y, and z. The best way to choose the parameter is to look at your system. What variable is missing a leading one? X has a leading one, y has a leading one, z does not have a leading one. Assign a parameter to z. Let's say z equal to t. After assigning a parameter into z, use the last non-zero, last interesting equation, which would be y plus 10 11 z equal to 0, and plug in the parameter z equal to t in there. So what would you get is y plus 10 11 t equal to 0. This results in y is equal to negative 10 11th of t. So this is as usual. If I had a unique solution, I would have a numerical value for z. I would plug it back into the very last meaningful equation and then solve for y and continue. Here, I don't have a numerical value. I have many values for z. T is a parameter that can run from negative infinity to infinity. I use that value that I found for z or assigned to z, and I plug it back to the last meaningful equation. Now, the next set is, now that I have assigned one value to z, solved for y using that, go back one up to the meaningful equation that comes before the last. That would be this one. And so in here, x plus 5, plug in what you found for y, plus 4, plug in what you found for z, equal to 5. And solve for x. So it's x plus, 5 times negative 10 11 is negative 55. Negative 50 over 11t plus 4t equal to 5. Put these two terms together. That is negative 50 over 11 plus 44 over 11. That makes it negative 6 over 11t. X minus 6t over 11 equal to 5, and that solves as by adding 60 over 11 to both sides. So using what parameter we assigned. We get a value for y. We get a value for x. I can also express this as 5 plus 6t over 11 negative 10t over 11, and t is the solution. What we discussed with unique solution, this means there were 3 planes in the 3D space meeting in one place, in one point. That would be this shape for unique solutions. Now, what does it mean for infinite solutions? In here, the other ways that 2 planes can meet each other are 3 planes can meet each other are one way is to meet each other on a line, or they can all coincide in the same plane. This is the meeting in each other in a line. So this is a line in 3D space. And we're done with this problem.